Okay, so well, it gives me a great pleasure to welcome Alok as our speaker this week. I had the good fortune of meeting Alok through, in fact, last week's speaker, Vikas Agarwal, who connected me with Alok when we were setting up the Data Science Center of Excellence at IISA Mohali. And Alok very kindly agreed to be on the advisory board there. And then I visited Hyderabad a few months ago, and Alok was very kind to come out and meet me at IIIT. And that was the first time we met, and of course it was a fabulous meeting because he's such a lovely man, in addition to being such a wonderful data scientist. That we really enjoyed meeting him. Me and my wife, in fact, really enjoyed meeting him. And he brought this, I remember, this wonderful book for me, which is his way of meeting new people, I guess. So he leaves us with a little present. So thank you for that, Alok. And of course, thank you for being a friend ever since. And it's always a pleasure to talk to you and hear from you. And the topic today, of course, is a great topic, the curse of dimensionality, something that we are facing more and more with the new types of data sets that we are dealing with. So I thank you for taking the time out on a Saturday to talk to us. And, there's a lot of excitement around to listen to what you have to say. So I'll hand it over to you rather than keep them awaiting. And I look forward to hearing your talk. Alok, you're muted.
All right. Am I audible now?
Yes, you are. Thanks.
Excellent. So first of all, thanks for giving me this opportunity, Sharabji and Sabut Foundation. So what am I going to do in the next maybe 40 to 45 minutes is try to understand what is curse of dimensionality, right? So that's one, and the whole objective of this talk is going to be to gently introduce, the what actually is curse of dimensionality. So we'll speak a little bit about, chaos theory or information theory a little bit, and then how does it become a challenge, right? When we talk more from data science applied AI standpoint, then how to manage this, this challenge, and if there are, latest developments that we can kind of apply in our work. So net, what the focus would be is just to kind of kindle the interest in these set of topics, which is again very pertinent from an applied AI modeling data science standpoint. So let's get going. So as we know, or we are aware, that nature always prefers chaos, right? So what do I mean by that? So chaos, again, those few who would have gone through the entropy theory, right? So any closed system actually tries to increase its entropy. So increasing the entropy means, again, disorderliness. So the more the entropy, the more chaos it has. And how does it translate into nature is, whether it is our universe, which is a big giant system. So there also, how does it really exist is in a multidimensional space, right? So so basically, if you see uh, in our mythology also, what happens is there is a mention of, or it's a conjecture that we do not in fact live in universe, we live in multiverse, right? Multiverse with at least 64 different dimensions, right? With a recent development in string theory, right? So string theory, superstring theory, you would find a mention of 26 dimensional space. Now there is a very recent, development in terms of what is called as Blue Brain project, right? So the whole idea of Blue Brain project is how do we really mimic, uh, human brain, right? So for that, the researcher researchers wanted to understand uh, the structure of the brain, right? So very interestingly, using algebraic topology, we you know they came out with the fact that human brains can go up to a structure of 11 dimensions with and very neatly packing up around more than 86 billion neurons. So basically, what we get here is the most sophisticated CPU ever built with the with the cheapest cost, right? So having said that, what happens is when we have multi dimensions, the challenge here, particularly for humans, is that intuitively we can perceive in at the most 4 dimensions. So that's called space-time dimension, right? But you know, closer home, 2 to 3 dimensions is what our cognitive abilities allow us to perceive it. So that's why the definitions that we have for, let's say, how how we define universe, right? So basically we say that universe has 3 spatial dimension, right? And then one temporal dimension, right? So what we have done here, if you see, is from a disorder, right, wherein there was too much of information available, right, too many dimensions available, to make it cognitively appealing or cognitively, quote unquote, making sense. What we have done is we have actually reduced it to dimensions which we can understand it in, right? So so basically, what we do in all of these is always there would be there would be a nice kind of trade-off between what is too much of info, what is too much of information versus how we can perceive that information. So so that's what is the whole talk all about. So let's move into the next one. So uh, those of us who are working in this field, we always get very excited if we have uh, too many rows and plus too many columns. So we will generally brag about, oh, I had this data set which was around 50 gigabytes, right? Um, so the so where what's happening there is that it is always better for us to have as many dimensions as possible from an information standpoint, because the more you getting dimensions, so essentially you are getting more information about that particular piece. So uh, but where it actually starts to become a little costlier is the kind of data that we would require to actually get all these dimensions. So so what, in a nutshell, what happens is the cost of having more dimensions may far outweigh the benefit of having that particular information available with us, right? So just consider a case of a data set which has around 1,000 columns, right? Now you are left wondering as to how how many of those are actually making sense, right? So that's one. Second thing is, if we come from a classical statistical standpoint, right? Uh, and we see the recent developments. We are always talking about black box models, right? So to me, personally, that feels a little oxymoronic. Why? Because model, the model, the term itself actually was coined to actually understand or explain the phenomena, right? So basically here, explaining bit is very important. So the moment we are saying black box model, that becomes contradictory in itself, because if it is a model, it should be able to explain it to you as to what it is doing, right? So from that standpoint, what happens is that our goal for any modeling activity has to be as to how to make it explainable, right? And to do that, again, what we would have to actually do is make it cognitively perceivable, right? And if we want to do that, how are we going to do that? We would have to actually uh, kind of compress it into smaller dimensions. uh, so before going into those, two very simple examples, just to understand as to why we in statistics call it a curse of dimensionality, right? So if let's say if you take a 2000 rupees note, right, and then you place it in a on a straight line of 100 meters length, right? So it's very easy for us to kind of figure out where that 2000 rupees note would be lying. Okay, so easy. Now, let's say if we increase one dimension only in this very simple problem, right? And then we say that, okay, we are not putting it in a line, but we are putting it in a plane, which is 100 by 100 length, right? So what is happening here is we are talking about a 10,000 square meter space where we are to find this 2000 rupees note, which becomes a little difficult for us, right? But then, again, uh, it is difficult, but not so difficult. And just remember that we have just added only one single dimension to it. Then let's add the third dimension, wherein we are talking about placing this 2000 rupees note in a structure which is 100 by 100 by 100 meters. So meaning length of 100 meters, breadth of 100 meters, and height of 100 meters. So now it becomes a very evolved sort of a problem, right? Because here you're trying to find a note, right? Which in a structure which is like uh, resembling a 30-story building. So the problem becomes really hard problem. Similar case is closer home if we go, and those of us who are actually working hands-on with the data, right? We always come up with the problem of finding out whether the customer would go for X or for Y, right? So let's start with that, right? So here we'll take this simple example of whether the customer would buy a car or a truck, right? So here again, very simple thing, and here we will maintain a data density of 50%, just just for this particular problem's sake. So here, to understand that, how and it's just one dimension, and the dimension is whether it is a car or a truck. So the property is to be either of these, right? So how much data do we need at a minimum? It is one data point. Now if we add another dimension to it, wherein we try to say whether the person is going for a red car versus a yellow truck. So what we have done is we have added another dimension to it, right? Which is the color of that object. So here what is happening is at the minimum, you would need just to maintain the same set of data density, you you will have to have at least two data points, right? So with that, this this would suffice. Same ways, if we add a third layer or a third dimension to it, so basically try to understand red car with sunroof or yellow truck with not without a sunroof, right? So here again, what is happening is at a minimum, we require at least 4 data points just to maintain again the same set of data density, which is 50%, right? So what is happening here is if you see, In the first case, we require only one data point. In the second, it is 2. In the third one, it is 4. So far so good, but the whole challenge lies when we go into additional dimensions. So we'll get there in a bit. So in general, to maintain 50% density in a space with n dimension, we would need at least 2 raised to power n minus 1 data points. Right? Now consider the case when we are going from a 20th dimension to 21st dimension. So basically we have 20 dimension data set, but we are going into adding up 21st dimension. So for that, at a minimum, we would require 2 raised to power 20 data points, right? So very easily, the problem starts to get out of out of our hand. And mind you, this is just, we are talking about only 20 dimensions. We are not even going for 100 dimensions or 200 dimensions or things like that. So that's where it starts to become a very real problem, right? And that is why a mathematician R. Bellman actually came up with this term of curse of dimensionality, because what happens is the volume just kind of overwhelms us. So that is one piece of it, right? The kind of data that's going that's required is just becoming humongous, because as we saw, just going from 21st 20 to 21st dimension, you need at least a million additional data points, right? uh, so that becomes one of the challenges, and very real challenge at that, right? So apart from that, you know uh, apart from the volume of data required, too many dimensions pose another very real problems. One is of course processing, second is of analyzing, and then finally, the how do you interpret it? Because again, as we had seen, we have limited cognitive ability. As Stephen Hawking said, that human brain, because of the evolution, human brain cannot really perceive more than 2 to 3 dimensions. uh, if there is a development in there, evolutionary, uh, we can go up till some dimensions, but not more than that. So because of these particular reasons, what happens is, we come up with a real challenge of curse of dimensionality, right? So I'll stop at that. Are there any questions till this point?
So Alok, there is a question from Mohan, or a comment actually. I think the solution for a lot of data science problems is within understanding our own mind, not only mathematically, but from physics point of view as well.
Yeah.
This is the dimension so far seems to be missing in research, so far as per my understanding.
No, not yeah. So very very pertinent point actually, because whenever I discuss this particular thing, uh, and not about the topic, but data science in general. So I always encourage them, as aspiring data scientists, we should always read about cognition, because that is what we are trying to do here in any data science problem or any applied AI sort of a problem, wherein we try to understand how how brain works, right? And what are the challenges it can pose. So yeah, completely with you on that. So.
But Alok, it's not just how the brain works, right? Because the human is an irrational agent. So the brain might be telling us something, but we kind of act with our hearts sometimes.
No, so that irrationality is brought in again by Hindi films more. Not, yeah. So jokes apart, yeah. So we we have not yet fully understood the brain, and we would not be at in near future also. Digital, as I was making mention of Blue Brain project, at till this point in time, what it has been able to achieve is just to understand the little structure of the brain, one single part of it, right? So it's going to take quite a while, because, and that's when I listen to the arguments that we would soon be replaced by robots, and it will have cognition and this and that. So you know that leaves me very amused, because cognition or consciousness is something which is really different ball game, rather than actually learn trying to train 3 or 4 or maybe 10 deep learning models, right?
Hmm.
So yeah, I mean,
There's
we can.
another, sorry, go on.
Sure. No, go ahead. Sorry.
There's another question which says, does having linked data or graph databases help in solving the curse of dimensionality? As it can be said, the human brain is a kind of graph database.
Right, right. So in graph database also, what actually you're doing, in fact, more so in graph database, you actually try to reduce dimension, because what you're coming up with, you're coming up with cliques, right? So cliques are nothing but dimensions. So in fact, the blue brain project, that again I am repeatedly mentioning it, actually used the graph analysis to come up with with 11 dimensional structure of the brain. So
I see. Okay, interesting. Um, wow, you're getting a lot of questions here.
yes.
So one question is, what exactly is cognition if I have to explain it to a layman?
Okay, so that's a very challenging, I mean, a very good question. So as they say in the films, if someone says it's a very good question, then that means he doesn't have an answer to it. You see. So, but I try my hand at it. Cognition again. Cognition is a faceted thing, right? So you'll have to see in what facet you are trying to define it. For me, cognition is something where where you can perceive things, right? So our machines are still not able to perceive, quote unquote perceive things, and that's why the whole hype around cognition, cognitive ability, uh, cognitive and this and that left me a little wondering, because if you see the IBM offering, they 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 actually name it as cognitive, right? But under the hood there is nothing really cognitive about it. So you're trying to actually, you have a supercomputer, right? And then you're trying to place it with a human brain, right? So it it is going to again, we have to also understand that how how advanced is our brain, right? The kind of dense this thing that we have in here. If you see the whole IBM supercomputer, the structure, it'll it will span over quite a few of clusters, and you will have the whole deep learning algorithms running behind it and all of that, right? So compare it with one person who's just walking the street, right? So so that's why I always I always get fascinated by nature as to how it has been able to pack so much of information in such a small space. So,
Hmm. Another question is, we are talking about reducing dimensions, but isn't the integrity and meaning of data change as we reduce dimensionality? So I guess you were pointing in that direction.
right. So, so the whole, whole thing is, so we always keep on doing that, right? So you and I understand that universe is a three-dimensional space, correct? But is it really? Is it just because we are able to perceive it in that manner, or is it something really different, right? So, same is the case with the dimensionality reduction thing, because what we are trying to do here is uh, there is all there is always going to be a trade-off between too much information versus optimal information, right? So we'll go into that section, once the question is done.
Okay, great. Thank you. There is another question, which is more of a philosophical question, I think. What's the difference between consciousness and cognition? So, which is a great question. But,
Yeah. So again, in fact, I wanted to make a caveat earlier that dimensions always have a philosophical and a metaphysical sort of a discussion, right? So I very bluntly wanted to put that out there, but great that we are actually discussing this. So consciousness is something very, I mean, in my view, consciousness is very different than cognition, right? So cognition is a subset of consciousness, in my view, right? Because cognitive cognitively we can differentiate A from B, C from D, right? But consciousness involves a lot more than that, right? So for example, again, taking that universe thing, are you able to understand as to how many how does it you know so basically, what is the original structure of universe, right? So is it really a three-dimensional space, or is it, as is said, or as it is conjectured by philosophers, our forefathers, it's a multiverse with n number of dimensions. So to me, that would mean consciousness, right? So again, just to differentiate, to a layman, what would be so a deep model, a deep learning model, right, would have cognition, right? When we are talking about a computer vision model, so it would have cognition in that realm, but it won't have consciousness. So
okay, we have another couple of questions here now. One of the listeners is pulling us back into the data science space and saying, is the curse of dimensionality a bigger problem in data science because we pursue correlations, or our understanding of causality a limiting factor to a large extent, and there are highly multicollinear variables or dimensions? Also, when we are using heuristics, do they reduce the dimensions? Sorry, I've lost that a little bit. But also, when we use heuristics, do they reduce dimensions by packing multiple sources of information into an easily and accurately observable metric?
uh, so great question again. See, when we are talking about dimensionality reduction anywhere in any of the model, the objective is how do we really perceive it, one. uh, and then the most important point is how do we do it so that we are not losing out on information, and that becomes very important, right? So it's always a trade-off between how much we would be able to perceive or would be able to make meaning of, versus how much information are we losing. So so that sort of a decision has to be taken by every researcher or the data scientist who is actually doing that. So in strict sense, for every dimension reduction task, we are actually losing some information, right? But not necessarily the optimal information. So basically, you are losing information, but you are not losing critical information. So if that answers your problem, question.
Great, thank you. I am aware that we're taking a lot of time here, but just one last question, sir. If we reduce, say, dimensions of a tabular data set, are we talking about removing columns specifically, or is there more to it?
Yes.
So I
Yes.
presume you might cover that in your talk.
Yes. Yes.
Yeah. Okay. Great.
So yeah. So unless and until I, specifically mention it, uh, whenever we are talking about data set for now, right now, it's always going to be a tabular data structure, right? And and again, what do what do I mean by dimension per se? Just for mathematics sake, is you know is a particular thing which can be defined by a minimum number of points, right? So line is going to be one dimensional because it can be described by, or a point can be found out in one this thing, right? So basically, if you plot a point, you will have a line through it, right? So uh, from that standpoint, we are talking about dimensionality. Now, in a tabular data structure, what is happening is you're taking a particular row, which is in there, and then columns actually always view columns as the properties of that particular row, meaning dimensions of that particular row. So what happens is, if you have too many dimensions, then cognitively you are not able to, and if you would want to go more into coordinates, right, or topology, it it becomes quite a bit of a challenge to really understand and visualize that, right? So so that's why after two or three dimensions, we just give a name to that particular phenomena where we have too many dimensions, and we call it as hyperplane, right? So all our models, I mean, whatever developments we have made actually in model building or coming up with new algorithms, they're not really that well equipped to actually kind of go through too many, or answer too many dimensions basically. So that is another challenge which is in there for a multidimensional data structure. So any further questions?
So there is a follow-up question here that says, but after removing columns, if we are learning from that data, can we really say that the good predictions are because we might be learning correlations from removed columns? I'm not sure I understand that, but he says, my question is, shouldn't there be a reverse relationship between dimensionality and interpretability? Uh,
Okay, yeah, so just to just to kind of answer, address the reluctance of the question, right? So it is, believe me, whenever you are actually reducing dimensionality, uh, of course, as you said, it's kind of slightly inversely proportional. So I'll not say it's directly inversely proportional, but slightly inversely proportional in terms of interpretability part of it. One. Second is, uh, if your reluctance is that if we really reduce dimensions, right, what's going to happen to our model accuracy, right? So there are proven studies which point out that after reducing the dimension by whatever means, we'll talk about some of them, right? So going from very basic to some sophisticated models if time permits, uh, what has happened is their accuracy measures have improved, right? So so what happens actually in in real life is what you might perceive as information might actually be noise and not the real signal that you're looking for. So by reducing the dimensions, what you're trying to do in a way is actually removing that noise as well.
Great, thank you, sir. I think we can take more questions later if you want to carry
Sure.
on with your content.
All right. Yeah. So as and these questions were very pertinent to where I was, where I was coming to, right? So to the to the last question which we just discussed about, right? So we are not saying here that dimensionality per se is the problem or multidimensionality per se is a problem. In fact, from an information theory standpoint, if you see, the more dimensions that we have, the more information we have, or the more randomness we have. The more randomness we have, the more variability we have, right? So how do we really, when we are modeling anything, right? What we actually do, have you ever thought about it? So what what I encourage everybody to do really is whenever we are modeling or whenever we are doing data science tasks, we should always ask ourselves as to why we are doing it, right? Uh, so when we are actually addressing, trying to get into model building, right? We we have to ask as to whether I should go by a brute force approach, meaning if I have gotten like 300 or 400 or 500 characteristics of a particular data set, I should just go ahead and dump it and model it out, right? Or should I really be thinking about it as to what does it mean? What's the kind of information gain that's going to be there, and things like that. Because we come from, and Dr. Sarab would also agree to it. We come from a very classical statistics standpoint, right? So there, it was actually grilled into our mind is a mind that uh, you know the golden rule, the golden rule of modeling is parsimony, right? So meaning, if we are able to build a model or explain a model in as few dimensions as possible, that model is the most optimal model, right? So, uh, so what I'm saying is one thing: multidimensionality or too many columns are not necessarily a problem, right? The problem is if those columns actually do not really add into the information or add into the variability that you are looking for. Because how you are going to model, you're going to model basis the variability that is contained into the data structure, right? Now, if there are candidate variables or dimensions which actually do not add anything to that variable, then why would you want to have it, right? So so thinking from that standpoint, how do we really address the challenge of multidimensionality? So there are two common approaches that people take, right? One is, as I was saying, select the most relevant dimensions. So that's one, and the second is create a smaller set of new dimensions. So we'll get into the techniques of each of these. So selecting the most relevant dimensions, we also, now very fancy, it has been given very fancy names like, feature selection and all of that, right? So back in our days, we just used to call it, okay, do we have this variable in our model or not, right? So um, talking from that standpoint, some of these steps are really, kind of very traditional classical statistics techniques, which to my surprise actually works quite robustly as compared to some really advanced high, heavy duty algorithms, right? So uh, so the first of it that we picked is missing value ratio threshold, right? So let's say if you have a data set, again tabular data, right? In that, you know if you see that there are just too many missing value pieces, right? So what do you really do about it? One thing is, as we would have been taught, or we would have actually done it, let's do imputation, right? Now there, again, you'll have to keep in mind as to how much of an imputation you should be doing, because of the simple fact that even if you are actually doing imputation, you're just filling up the data set. You are not actually creating, or adding any variability to it. So, so basically, let's say if you have missing value pieces, right? And then if you are not able to add any new variability, first of all, adding new variability is going to be, going to play with the data integrity part of it, right? So you would not be doing that. Imputation, what does it do is it just kind of spreads that particular thing with little, minimum to no variability. So if missing value is too, too widespread in the data, in the data set, in some of the columns, right? Then the best way would be to actually select a threshold, right, by which, you would be able to decide that, let's say, if the missing value ratio is more than 40% or more than 50% or more than 60%, or, depending on how your problem is. I mean, all these again are again not a rule of thumb things. I just took examples. So if the missing value ratio is going to be too much, right? One, it doesn't add, it doesn't really add any additional information to your data set. Second, select a particular threshold through which you can decide that we will not pick up any, or we will not select these dimensions which have missing value ratio above our threshold. So that is one of the strategy that can be employed, before actually you go ahead with a model building. Now the second one is low variance threshold. Here again, as I was saying, is the whole purpose of bringing new dimension is, or having new dimension is, to get additional information about the data set, right? Or adding in additional variability to the data set, because this it is this variability, which we are using to actually model it or say something about, about the whole phenomena, right? So if there are columns which have, again, a very low variance, right? And again, you can decide as to what is your definition of low variance, right? So for example, if, if you have a column which has, which really doesn't have any variance in it. So it's, let's say, it's, if it is 1 1 1 1 1, it just is 1 1 1 1 1. That's it. And maybe it's 1.2 or 1.3 once in a while, but that's about it, right? So then that means it has a, it has a very low variance. Now the the challenge with that is it's not going to add anything to the, uh, to your data set, or the sample space. So the best way would be to actually get rid of that particular thing. Here also again, the suggestion would be that you decide a threshold, right, and say that if it is below this threshold, we are not going to have this. So that's second one. Then the third one, and we had a question regarding this particular thing, is high correlation threshold, right? So why we keep this high correlation threshold, right, is basically when there is a very high correlation between two variables. So there is this phenomenon, so that is a technical name to it. We call it linearity between these two variables. So if linearity is there between these two variables, the best bet for us is to take either of these variables. Why? Because of the simple fact that the kind of variance addition that either of these two should be doing is just as much if, one of them is there. So that's why we should again decide about a threshold for high correlation. So let's say whether it should be more than 0.75 or 0.85, zero point 0.9, what it should be, right? And then, take those variables which have a very high correlation and take one of them basically, right? So so these are again very old but methods, but these are really like war horse, right? Then going forward, there are two more. One is backward feature elimination. So here, basically, you are actually taking all of your variables, right? And do the modeling. And then here, actually, you are getting into something called as iterative modeling, right? So uh, you take all those through 200, 300, 400 variables, model it out, try and see as to what's happening. Then, kind of remove one of them, again model it, see whether there has been some change in the predictive accuracy or the model parameters, uh, and then keep on doing it, unless there is no real change that is coming. So that would be your backward feature elimination. Forward feature selection is exactly opposite of it. So what we do is you take each of these columns, model it, right? And then start with that particular feature or dimension, which is kind of explaining the highest variability. And then keep on adding it, keep on adding other dimensions and keep doing it till such time when addition of a particular variable is not actually going to change your model parameters. So that is what is called forward feature selection. So there is another bit in which you go one step forward, one step backward. So we'll not go into that, but overall, these are the techniques which we go for actually considering which of these variable, which of these dimensions or variables should be there finally in our model or not, right? The last one is again random forest. So with the ease of computing power and all of that, what people do these days, and I think we can do that. I'm not commenting on that particular thing, but here run a random forest ensemble, right? And then see the feature importance, right? And take those features only which are really important for the model, and then go for the next step of modeling. So I'll stop at that. There are some more, but I'll take up some questions and then we can go forward.
Any questions? I guess when we talk about backward and forward feature elimination or selection, we're really doing a search in the subset of all features, a space, which is defined by this, the subsets of features, right? Is there a danger in kind of taking this greedy approach of just kind of dropping the least impactful feature each time, or adding the most impactful feature, that you could end up with a suboptimal feature set there? Or
Yeah, so that's the kind of challenge that is going to come at times, because the very nature in which it has been built, kind of that kind of an error can creep in. So that danger is there for sure.
Mhm. Okay, great. Thank you. There aren't questions at this point, so
Okay.
you can carry on. Yeah.
All right. So let's go to the last bit of my slide. So below are some advanced techniques. So why I'm saying advanced is because here you will those of you who are data scientists, but you are not very friendly with, let's say, linear algebra, right? So from that standpoint, it becomes a little advanced. So because here we are talking about matrix multiplication and stuff like that. I'll not go into any of that. The But why I'm highlighting this is because the basis for all of these is matrix algebra, and it will do well for those of you who are either starting or have already started, to actually refresh your matrix algebra basics. So having said that, again, let's go into these techniques. So what these techniques do and why I have separated it out with others is very simple. Here what we're trying to do is we're trying to actually create new variables, which might be underlying the observed variable that we have. What we do is, let's say you have around 300 or 500 variables. So we are trying to see out of these, so whether there is something underlying this, right? And if it is there, can this be a good proxy for to be put in our model, right? So essentially we create new, we create new variables. So we have the variable structure, the variance structure. So basically what we are trying to do here is we are trying to actually restructure the variance space. So so principal component analysis is something you know that 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 we do, and it's fairly common. There's quite a bit of, or not quite a bit, I mean, there is a bit of a confusion between principal component analysis and factor analysis, right? That might be because of, again, the way software vendors, do it. So they'll put principal component analysis under factor analysis, and so on and so forth. So the goal of that is, again, principal component analysis. For what we are trying to do here is we are trying to actually come up with a structure in which the dimensions are orthogonal in nature, meaning they do not have any correlation whatsoever. So basically, if you try to understand uh, kind of coordinate geometry, right? So after principal component analysis, your your dimensions would be structured at, orthogonal to each other, meaning kind of having a 90-degree angle to each of them. So that's what the thing that we do in principal component analysis. Again, not going to too much of details as to what is the rotation and stuff like that, but just to provide a very simple introduction to it. So objective of principal component analysis is coming up with new sets of variables which are orthogonal or not correlated to each other. Now, again, here the assumption is, and if you would have heard me, what I'm saying is they are uncorrelated in nature, right? So whenever we are talking about correlation, again, underlying assumption of correlation is linearity. So they are linear in nature. Now, what if the dimensions are not linear in nature, right? So so in that case, what would happen is, or how do we say that the component that we have come up with are still not related, right? So for that, we'll go with independent component analysis. That's a new one. But here, what happens is, even though, let's say, the dimensions are not linear, but after doing independent component analysis, right, you you come up with components which are independent of each other. So just try to understand the nuance in principal component. What we are saying is we are coming up with uncorrelated structures. In independent component, we are saying that we are coming up with independent structures, right? So that's the real difference between principal component analysis and independent component analysis. The third one is singular value decomposition. Again, you come up with a structure which is, again, orthogonal in nature, right? So principal component analysis, in a way, is is a special case of singular value decomposition, right? And if you were wondering as to which softwares to use to do that, and all that fun stuff, I think most of these have already been implemented either in Python or in R. So Python, I'm more sure of that they are already there. Now, these you know these three are, again, talking about orthogonality, talking about how do we really recreate the variance structure. The last three, which is like TSNE, UMAP, and factorization machine. So factorization machine, very interestingly, has been proposed just I think 18 months back, and it really works very well. In very large data sets. So so we'll come to that in a minute, and we are anyways on top of our. So I'll just take 2 minutes to explain and give some tips onto where to use what. So TSNE is again good, but it's very computationally, a little computationally intensive, right? So also it works well in the present data structure, right? So TSNE you should, you can go ahead with, but then keep in mind that it's again computationally intensive. UMAP is a, again, projection based technique, right? So uh, here UMAP works better than TSNE, right? So and faster as well. So if you have a chance to apply TSNE and UMAP, I think UMAP is going to work a little better. Just to give a one liner about how mathematically it works out is, you know so basically, let's say if you have two vectors A and B, right? And then if you'd want to actually project A on B, so there would be an angle that you would have to put through, and then, you know then you can have A hash, which will be A into B cos theta or something like that, right? So that is what is the core of TSNE and UMAP, right? Although again, I am not expecting all of you to really go ahead with uh, the real mathematics behind that. But yeah, a higher level, what happens is a higher level understanding of mathematics really works well when you are trying to apply it. And and the most important piece is that if you know at a higher level as to what is under the hood, again, no derivations or some such thing, but if you know overall as to how it is working out, then it becomes very easy for you to first understand as to where to apply it, in what situations to apply it, and what do we get from it. So meaning, uh, you know you can really answer the so what piece of it, that if we want to make sense of what is coming out, whether it is good, bad, ugly, that that journey is going to be very easy. So I'll stop at that. I thought I'll finish it in 45 minutes, but I just went over time, and we can take up some questions if
Yeah, we have no problems with you taking more time, of course, because we are enjoying learning from you here. There are a number of questions here. So the first one is, in TSNE, what role does stochastic play in the projection, uh, in randomized allocation of weights initially, or something else? I'm not sure I understand the question completely here. Um, um, It says, what role does stochastic play in the projection in randomized allocation of weights initially, or something else?
okay.
Okay. Um, the other question is, what is the difference between uncorrelated and independent?
Hmm.
This is a good question.
That's yeah. This is a good question because I can answer it confidently. See? So that is what I tried to actually explain when we are talking about PC and independent component analysis. So so uncorrelated. So generally speaking, what happens is, when we are modeling, right, we generally assume that the things are going to be linear, right? So that's why the majority literature, or the majority discourse actually equates uncollinearity with independence. right? It might not be the case, because if you see the correlation thing, the correlation measure itself assumes linearity, right? So what if the, if the structure is not linear in nature, right? So then even if, let's say, even if it is uncorrelated, right, it might not be independent, right? So that's the kind of nuance that is there.
Great, thank you. Um, I'm trying to interpret the earlier question still. I'm not going to give up on that, but I think it's to do with the name, right? The t-distributed stochastic
Yeah,
neighbor embedding. So
yeah.
I think the question is, what is the stochasticity
Doing
within?
here,
Yeah,
yeah. So stochastic, I mean, again, very simple definition of stochastic. It's kind of memoryless, right? So what do I mean by that is, it doesn't really take history into account, and then does it, does its job, right? So
right. In fact, Rohit has just, who asked the original question, has reframed his question. So thank you, Rohit. I think, we kind of figured it out just in time. Vishal Soni, he says this might be a silly question, and of course, there's no such thing as a silly question, but very
exactly.
useful for aspiring data scientists. What is best practice with missing values, deleting them, or I think the word he wanted to use here was imputing rather than iterating them.
Right.
If iterating, then what is the best criteria, mean, mode, median, or something else? If you can throw some light on this.
Yeah, sure. So and my son is trying to Zoom bomb. So
Yeah, great. Excellent. Good to see him.
I'm sorry. So so see, again, the point is that uh, when we are talking about missing value, missing value. I'm sorry.
No, no, no worries.
Yeah. So when we are talking about missing value and the strategies to deal with missing value, right? So imputation is yes, right? Again, why I said you take a threshold and then take a decision whether to keep it or not to keep it. So let's say if if the missing value is to the extent of, let's say, 4 to 5% or 7%, uh, then of course imputation is the best bet, right? Because you are just trying to fill the values with, without tinkering on to the underlying variance structure, right? So that's what we should do. Now here again, how, which one to take, in terms of imputation, whether it is mean, median, or mode, or whether it's a localized optima that you'd want to take, is again left to your discretion, with a caveat in mind that you should be taking that particular measure which best kind of represents the variance structure, you know locally, right? So that's one thing that we have to keep in mind while imputation. So like one very sophisticated model is mode that you can use, but then you'll have to see, you'll have to first understand about how is it again going to play with the whole variance structure that you have.
And how important is understanding first why we have missing data in the first place?
Exactly. So that's why, my advice always would be to all the data scientists is, it's not only science. It's in fact, if I had my way, I would have called ourselves as data artists rather than scientists, because because
Yeah, I like that.
most because most of the times it's an art, because you're trying to understand it, you're trying to see as to which is going to be making more sense, less sense. So I think, when you are modeling it, or when you are doing these kind of activities, that's where your whole passion should be there to. And if the passion is there, then you would have so much of curiosity and interest to see as to what stands for what, and that's why you will do XDA, right? So right now many of us do not really want to get into those, right? We just want to have a clean data set and then just do some some modeling, right? So that's not how it's going to work, because please understand, and most of you anyways would have understood by now, that out of, let's say, 100%, 60 to 65 to 70% of your work is trying to understand the data, right? And that's not going to go anywhere, because if even even if so many developments that would happen, let's say data robot or some such thing, it's still, or auto ML and other things, it's still is going to be left to the person to kind of understand as to what does it really mean.
Right. Thank you. I'm going to come back to Rohit's question because he's the one who asked about TSNE, and there are a few follow-up questions there. But let me just take these smaller questions earlier. So one question is, please correct me. Let us say that we want to replace missing values. Then if variance is high, we use mean, otherwise median.
Then if the variance is high, then then I think that uh, the variance might be because of some outlier value, because if the variance is high in that particular column, right? So in that case, the best bet is going to be median.
Is going to be median.
Yeah.
Okay, but in general, of course, what putting the mean in there would be is reducing the variance artificially,
Right.
right?
Right.
So that is probably not such a good idea in any case, and you probably
Correct.
want to take. Ultimately, you want to take the probability of that missing value given the other variables, right?
Exactly.
So you can
Exactly.
explain the
Yeah.
variance a little bit.
Right.
Okay. Okay, so now I'm going to come back to Rohit. So Rohit, and I'm posing this question to you, Alok, because I don't know the answer to it, right? But so he says in TSNE, it says T distributed stochastic mapping. Does it mean that the weights are allocated along the T distribution for initial weight allocation to each component as a starting point? Can we have T distributed fractal mapping of sorts? Can we use properties of fractality for dimensionality reduction? And are there methods to test if a variable is fractal versus stochastic?
Yes. So there is another technique which which I did not mention here. Again, just not to kind of overwhelm all of us with that. It's called isomap, right? So maybe isomap is something that you're looking for, right? So so very well possible. Another thing is, see, these are some of the techniques which are in there. Uh, Overall, what we have to ensure, right, is, and we can as well come up with our own method of dimensionality reduction. Just two things that we have to keep in mind is, one, it actually reduces the dimension, meaning if you set out to if you had n as your number, right, you go with m, and m is, of course, the understanding is lesser than n. One. Second, the total variability which was in there is still accounted for to a larger extent. So let's say if the initial structure had 100% variability, you are still able to account for around, I'll be very realistic. I will not be like Kaggle data set. Able to explain the majority of that variability, meaning, rule of thumb again is 70 to 75%. But again, that depends. That if you are losing out on that 25% variability, how many dimensions? So that's the kind of thing that you have to keep in mind. And then basis this, we can go go with very robust combinations or very robust algorithms which can specifically suit our purposes. So here these are some of the families of algorithms or the people who have proposed that, right? So we can we can use it as a wrapper based this thing and be done with it. But yes, those of you like who are interested in that, uh, that's why I was talking about trying to learn the mathematics behind it. Just keep in mind these two, or have these two rule of thumbs in mind, and then maybe you can come up with your own algorithm for all you know.
Great, thank you. There's another question which says, how do you choose any technique on a particular data set?
you know so that's interesting. Again, that depends on different factors. One is again, how big or small your data set is, one, right? How evolved you want to make it, what are the underlying assumptions of your data set, right? So like for principal component analysis, reality, linearity is assumed, Gaussianity is assumed, right? So there is another, another technique which I did not make mention of, because again, those were like very, very strict in terms of assumption, which is linear discriminant analysis. So LDA, QDA, uh, these bits are, you know, those are like what's called as parametric methods, which have, which have very tight assumptions, right? So you have to see as to, which of these assumptions would still hold, and then you can go ahead with it. So I would not expect any of us to actually do all of these together and then come up with something. No, that's not what the case is, right? So factorization machine, for example, the one that I just talked about, it really works well for huge data sets, right? So if you have um, data set which has around 100 to 200 variables, I mean, you just give it a skip. Map based projections like UMAP, TSNE, these are again, if you think that the data set is not, the linearity is not assumed, or the linear relationships are not there, then these work a little better, right? So likewise, each of these sets would have certain assumptions. So I was talking about random forest or ensemble models. So there, the best part is those are like non-parametric, meaning they do not really have too many assumptions, because again, the constituents of ensemble model is decision, decision trees, right? So which does not really assume distributions or other things. So there, that you can straight away employ and come up with factors which which are significantly impacting it, and put that in model. So net, uh, the best bit would be if the data set is small, right, or medium size. You would want to see, first of all, uh, which of these kind of makes sense, and then go ahead with it. uh, just another caveat to keep in mind is both uh, backward elimination and forward propagation. Both of these are very computationally intensive, as you would have seen, because you are iterating the models, right? So you'll have to see those would work only with smaller data sets. So these are certain working rules that we have to keep in mind while we would employ any of these.
Great, thank you, Alok. There is another very interesting point made here. Can explainability be an aspect of modeling with reduced dimension, Alok?
Yes, and that is what I also wanted to talk a little bit. Given the, I mean, we didn't had time. So let's say, and I'll take up one very interesting work that we had done. Now it's 10 years. So there, 10 years back, we were working with a US client, wherein we wanted to understand the impact of different marketing channels, right? So radio, TV, and other things, right? So there, what was happening was they, we said that okay, some of these are showing a higher correlation, right? So let's kind of combine it and then run a model. But there was a quite a bit of a pushback from them. So basically, we wanted to run a PCR, principal component regression, on that, because there was a higher correlation between variables, and then collinearity is becoming a problem. So when we went back to them, they told that okay, even if, let's say, if you run a principal component regression, how is it going to make sense to my chief marketing officer, right? Because you have a derived variable which is a combination of, let's say, TV and radio. So how do I understand the effect of, let's say, TV or radio, right? So that's why uh, when we are doing these, we have to also keep in mind the explainability bit of it. So finally, what we did was, we went for a technique called nonlinear constraint ridge regression, NLCR. So from the, at that point, it, it was uh, it was a really evolved sort of a model, but we were finally able to kind of do it. So any of the models are good model, are good models only when you are able to explain the phenomena. As I said in the beginning of my talk, that model itself, is, the word model itself means how am I able to explain this phenomena. So explainability is going to be the key in any modeling exercise. And so that's why you would have you would have seen there is so much of development which is happening around explainable AI. So
Right. And I guess that leads into this question from Rohit, which he claims is off topic, but Rohit, it's not. I think this is a great question. How much does auto ML reduce the role of a data scientist and thereby increase the importance of a data engineer? Um,
okay, so see, first of all, I understand this, this COVID-19 all over the place, and we are worried about our, our job, and I, myself included, right? So, so the point is again, it's not going to. So believe me, friends, none of these are kind of, as of now, none of these are replaceable skills. To some part they are, but not for the most part of it, or all of it. Why? Because auto ML is going to do what, right? Auto ML is going to run a model. So basically, what it removes the, let's say, the drudgery of actually import OS or import pandas and things like that, right? And then run the model, give the output. Now, a data scientist or a data engineer, and by the way, I do not really differentiate between a data engineer or a data scientist, or for that matter, quote unquote, machine learning engineer, right? So the point is that data scientist, or maybe a data engineer, or a machine learning engineer, right? So they have to understand the complete value chain, right? And any of these auto ML thing, auto ML developments, they are going to address or answer the part of, only a part of the chain, not the complete chain. So basically, let's say when we start out with a project, right? So at that point in time, do you think any sophisticated deep learning sort of interface is going to replace what actually is needed? So how is it going to really translate a particular business problem to to a data science problem. I would, because there you would need more more cognition, and again, going back to our discussion earlier, the consciousness, right? So so you'll have to make sense of it, and that's why uh, you know we should always be not only thinking about, let's say, what is the new pandas library, but also should be thinking about what's going to be the business impact of it, right? And that's very, that's very important. uh, what does it tell me, right? So so I do not really see any of that thing going, because now, people said that, okay, data and do not really go by all these fancy headlines, from Bloomberg or Washington Post, or some such thing, um, which used to say that, okay, now data robot is going to make data scientists, jobless, right? So so that's not how it's going to happen anytime soon, believe me.
So I'll make a facetious comment that data robot can probably replace a Kaggle competitor, but not a data
Exactly,
scientist.
exactly, exactly,
So you can
exactly.
do
Yeah,
hyperparameter tuning, of course, and that drudgery goes away.
right,
But real world problems are very different,
right,
right?
right,
You have to
right,
understand the business, you have to
right.
understand the data sources, you have to bring it together. I mean, so I guess if you're differentiating as a data engineer, because you have to pull that data together and create that initial input to your machine learning, that's a fair point that, the data engineer is going to be an important piece. But I think, as you said, there are a lot of aspects of even, um, you know, creating that data set in the first place, which requires a data scientist thought process. Um, there is another point being made here, which is, does dimensionality reduction lead to a surrogate model creation for better interpretability using techniques like Lime?
Yeah, so Lime is not a technique, by the way. I mean, Lime is trying to understand trying to understand the understand a black box model, right?
Hmm.
So and the proposers of, Lime, and I remember 3 years back when two of uh, they were doing the first webinar just to gauge the reactions from data scientists. So I was in that webinar 3 years back, and it is, Lime is just to actually support that. So basically, how to make how sorry so how to make
This is very strange, man. This is very strange, man.
1 second.
No worries, no worries. I think he wants you back now on a weekend. Sorry, Alok, you're muted.
Yeah, I'm really sorry.
No, no, no worries.
So yeah, so what I was saying was, Lime is, again, guys, please understand, Lime is something which is in addition to what you're doing, right? So this is more to explain to a person. So basically the business user, as to whatever you would have done in a fancy neural net model, for example. So how, so to understand the impact of a particular dimension, right?
Hmm.
So that is what Lime is used for. So it is not necessarily a replacement of what you're already doing, right?
Right. So I guess the question, as I understand it, Alok, is that say we do principal component analysis and we have a new feature set now, right, which is created out of the original input. Now the original input is what is understandable to the business. The principal components are not. So I guess the question that Mohan is asking here is,
Oh,
can
okay.
we somehow incorporate, Lime to give explanations back at the feature level, the original feature level, rather than at a principal component level?
So yeah, so Lime might be used, I would have to again see as to how much of development they have made in that. But back that time, it was restricted to neural model, neural nets, because that was
Ah,
supposed to be the first black box that they wanted to crack, right? And
right.
and they take the local this thing. Although the under the hood mathematics there also is very simple, because you take the local variables and then do a mathematical
Perturbation of it,
uh,
right?
yeah, and then say as to how it is impacting, right?
Right.
So however, using it for PCA, I would say would be would be too much to do using Lime, because Lime is for black box model and PCA is not supposed to be a black box model in the first
But
place.
in a way it is, right? I mean, any dimensionality reduction is creating a black box like you were maintaining. So it sounds like an interesting extension of what has been done with Line.
Right.
In fact, there was this question that came up, in our discussions in Sabud a couple of days ago, where we had built, or the students had built a model for predicting toxicity of a comment, right? So then we were actually using some methods for explainable AI to actually explain why a particular comment was classified as toxic or non-toxic. A question came up there about, what if we are using word embeddings, right? You would Line would essentially tell you that this particular dimension in your word embedding seems to be prominent whenever you made a toxic comment, but it doesn't really identify the words itself,
Correct.
right? And I guess in a similar way, if principal components was being used, you can actually think of the principal component structure also being kind of a graph structure where you're putting the inputs and then of course creating the principal components as a linear combination of your input structure and try and explain them with Line, right? So do you think it's something for Mohan to pursue?
Yeah, I mean, to me, that sounds interesting, but but because PC, you'd you'd want to do it for a little bit more evolved model than principal component, because my assumption is that it's you can very easily revert to your original variables in this case. So.
Right. Okay. Okay. All right. Thank you. So one thing, Alok, just before we finish off here, I do apologize because we've taken a lot more of your time than you had promised to give us. But you haven't mentioned autoencoders or the way we actually identify maybe even in RNNs, recurrent neural nets, we identify a hidden state, which is also an embedding, right, and a
Right,
lower dimensional
right,
representation of sentences or whatever it
I
might be.
yeah. Yeah, so I wanted to go from in the order of uh, very basic to really advanced, and then that's where I stopped basically. So
Okay.
it but yes, autoencoder, the word embeddings, all those are supposed to be again a dimensionality reduction techniques basically.
Right. Okay. But that would be for another day.
Yeah,
I do appreciate, Alok, especially given the circumstances today. You informed me of your dear friend who had passed away. And I really do appreciate that you still took out time for us. Thank you. And we're all praying for, the departed soul and for, peace to come to you and all his friends. So thank you again for taking out the
thanks so much.
time under these very difficult circumstances and really appreciate it.
Thanks
Thank
so
you.
much. Thanks.